Welcome to the math section of Chapter 4. Here we're going to detail all the calculations that we're going to be doing for the rest of this chapter. I decided to switch the order with which the chapter is presented, so instead of starting with math and moving into reactions, going from reactions and then moving into the math. And the reason why is because stoichiometric calculations, stoichiometry, all stems from having a balanced equation. From this equation, we are able to get what's known as the molar ratio, or the mole ratio. And that's the ratio of two different compounds and how many moles of one compound will form how many moles of another. This is a key theme in all the stoichiometry that we're going to be doing. So the first type of stoichiometric calculation we can do is to calculate the limiting reagents. You guys have already had some experience doing this in lab, and so here we're just going to expand on what you guys have done. So here what we need to do, so to calculate limiting reagents, we need to use, again, the molar ratio from a balanced reaction. Without a balanced reaction, we cannot calculate limiting reagents. So let's look at this equation. Every time I put up an equation, you guys should try to characterize it as one of the equations that we have talked about earlier in Chapter 4. So this comes from number 37 at the end of Chapter 4. And what we want to know is, what is a limiting reagent? So we have 2 moles of sodium, and we're given 2 moles of bromine. So, when we see moles, our first inclination is to turn them into grams. And that's a very good first inclination, except when we're doing limiting reagent problems. When we do limiting reagent problems, we should keep them in moles. So here we have 2 moles sodium, and we have 2 moles of bromine. So when we do these limiting reagent problems, we have to pick which product we're going to form. In this reaction, we only have one product, so it makes it a little bit easier. So we use our molar ratio to determine how many moles of sodium make how many moles of sodium bromide, and how many moles of bromine makes how many moles of sodium bromide. So we know for every 2 moles of sodium, right, because we have 2 moles of sodium, and that makes 2 moles of sodium bromide. So we know for every 1 mole of bromine gas is going to make 2 moles sodium bromide. Do not try to predict what the limiting reagent is until you start doing the calculation. So we know we make, these will cancel out to 1, so you have 2 moles sodium bromide, and here we'll have 4 moles of sodium bromide. So the limiting reagent is that reagent that does not give you the most product. So it limits your ability to make product. And so in this case, the limiting reagent is sodium. We can do other calculations with limiting reagents and molar ratios. So another type is we have iron 3 oxide, and we're going to react it with carbon monoxide. So I am giving you guys all of the balanced equations, or the book gives you, at least for these examples, the balanced equations. You might have to, when presented with an equation on an exam or a quiz, make sure that it is balanced. So these are already balanced. This is question number 47. And so what we have is we react 22.55 grams of iron 3 oxide to 14.78 grams of carbon monoxide. And we want to know how many grams are left over. Of either iron 3 oxide or of carbon monoxide. And so, the first calculation, so whenever you're given in grams, we want to find moles. So, we have 22.55 grams Fe2O3. The molecular weight of iron 3 oxide is 159.7. For every 1 mole. So now here we use our stoichiometric relationship. So we know that for every 1 mole of the iron 2 oxide, now we have 2 products. Which one should we pick? We should pick the one with the lowest number of moles. 1 if possible, 2 if you can't help it. So we make for every 2 moles of iron. So when we do this calculation, we find that we make 0.282 moles of iron. So we're going to do the exact same thing for carbon monoxide. So we know 14.78 grams of CO. And again, don't try to assume that you know which one is a limiting reagent based on weights. Do the actual calculations. So how many moles of carbon monoxide does it take to make how many moles of iron? So we know 2 moles of iron, and so it's going to take 3 moles of carbon monoxide. When we do this calculation, we get 0.352 moles of iron. So which one is the limiting reagent? The limiting reagent is iron 3 oxide. So the temptation will now be to figure out how much leftover carbon monoxide we have is just to subtract these 2 numbers. Do not do that, because we're not looking at moles of the reactants, we're looking at moles of the product. So that would not give us a true representation. So how do we determine how many moles of carbon monoxide are left over? There's 2 different ways. Or actually, there's only one way that I'm going to show you here. So, we know we have, let me erase all that. We know we have 22.55 grams of iron 3 oxide, and that is our limiting reagent. So we can turn that into moles, like we did here. But this time, instead of converting it into moles of iron, we want to convert it into moles of carbon monoxide. Right? Because we know that for every 1 mole of iron 3 oxide, we're going to have to use up 3 moles of carbon monoxide. So when we do that, that will give us how many moles of carbon monoxide we've reacted. So once we find this will give us how many moles that this iron will react with. And so when you do this calculation, we find out that it is 0.4236 moles of carbon monoxide. So now we need to know how many moles of carbon monoxide we have in 14.78 grams. And so when we divide by the molecular weight of 28.01, we know that moles of CO to react is 0.5277. Now we can subtract this 0.5277 from 0.4236 because that's all that the carbon monoxide that will react. And when we do that, we have 0.1041 moles. But if you remember, the original question was how many grams. So we multiply this by the molecular weight of carbon monoxide, and we get 2.914 because we get 4 significant figures, grams that are left over. I know it's a lot, but again, it's just like the combustion. Step by step by step through the whole equation will help us find everything else. So, one more question dealing with limiting reagents, and what we're going to do is we're going to ask the question, what is the theoretical yield? And so here we have a net ionic equation, or an equation showing a reduction So what we're going to do is a single displacement. And here we're just showing the ions. So we're going to react 25.7 grams of lead to 28.5 grams of potassium chloride. And so what we want to know is what is the limiting reagent and what is the theoretical yield. And then we'll do one more calculation after that. So we're going to do what we've always done, how we always start these problems. I'm going to start with potassium chloride. And here we're going to have the lead 2. We're going to convert them into moles, and then we're going to use our molar ratio to determine the theoretical yield. So again, do not assume that you know what the theoretical yield is based on molecular weights, because we want to make sure that we have it right. So I could stop at this point. So if you've noticed, I'm calculating the product of the lead 2 chloride. So I'm calculating this. And so what I want to do is maybe take it one step further. And here's the reason. Whenever you are asked to calculate theoretical yield, you need to calculate it in grams. And so if we stopped here, we would be able to find the limiting reagent, because it'd be the one that gave us the less moles. But if we go ahead and do one more step and turn the moles of lead 2 chloride into grams, then not only can we find out the limiting reagent, but we can also find out the theoretical yield. It will be the same answer. And so why don't we go ahead and do that? So the last step will be the same for both sides. And so what I'm going to do is I'm going to put the answer at the beginning, since I ran out of space. Alright. So we know for potassium chloride, what I started with, that's going to give us 53.2 grams of our product. The lead ion is going to give us 34.5 grams of lead chloride. And so whenever we're given a question asking for a theoretical yield, the yield that's given from the limiting reagent is also the theoretical yield. So let's get rid of some of this. Alright, so this is not only the theoretical yield, but it's also the limiting reagent. Now, let's say we do this experiment. We go into the lab, and you guys find out that when you do the experiment, you get 29.4 grams of lead chloride. We want to know what is that percent yield or percent recovery? So what we do is we take our experimental, which is 29.4 grams, and we divide it by our theoretical. So this is why we calculate theoretical yield, is so we can find percent recovery. .852 times 100 is 85.2%. So that's our percent recovery. So these are all things that we can do with theoretical yield. Theoretical yield, limiting reagents, percent recovery. I want you guys to do numbers 51 and 45 just as extra practice, and that'll be due Wednesday, September the 19th. So it'll give you a few days to work through some of these problems. Before we move on to molarity, per some of your requests, we'll maybe take a 20-second music break. Alright, now we should be ready to continue on. So we can use molarity to describe how much is in a solution. Right? So molarity is a capital M, and that equals moles per liter. So it's a bridge unit. Again, we talked about bridge units, bridging between amount and volume. So number 53B, we want to know what is the molarity. So we have a 28.33 gram glucose solution, and we're going to dissolve that in 1.28 liters of solution. So we want to know what the molarity is. So we have 28.33 grams. So we want in moles per liter. That's molarity, and that's what we're trying to find out. So the molecular weight for glucose is 181.07 for every 1 mole of glucose. If we solve that, we get 0.156 moles. We're going to divide that by the 1.28 liters, and that's going to be 0.122 molar. So if you noticed, my answer is in 3 significant figures because our volume was given in 3 significant figures. We cannot use the mass to give us 4. So if we can find molarity but from grams, we can use molarity to help us find how much grams are in a solution. So we have 400 mils of a 1.1 molar sodium nitrate solution. And we want to know how many grams of sodium nitrate are needed to make this solution. Here is the key. So just like with molecular weight, to go from grams to moles, we divide by the molecular weight. From moles to grams, we multiply. Here, if you ever need to find the number of moles, because we have to find the number of moles first before we can know the grams, to find the number of moles, you take molarity times volume, and it will always give you in moles. Now the volume has to be in liters, so that's the only one kind of exception that we have. So molarity times liters, or volume in liters, is equal to the number of moles in a solution. So here we have 0.4 liters, because remember, for every one liter there is 1,000 mils. So to go from mils to liters, we divide by 1,000. So we're going to take that times 1.1 moles, and that will give us the number of moles of sodium nitrate, which is 0.44 moles. And then again, we go from moles to grams, we multiply by the molecular weight, and that gives us 37.4 grams sodium nitrate, right? So a lot of these calculations using molarity are very, very straightforward. So let's complicate it just a little bit. So we can use molarity in stoichiometric equations. And so let's say we have potassium chloride plus lead 2 nitrate. And so that's going to go to lead chloride plus potassium nitrate. So we have a balanced equation here. And so what we're going to do is we're going to react 25 mils of potassium chloride, and the concentration of that is 1.20 molar, with 15 mils of lead 2 nitrate, and the concentration of that solution is 0.9 molar. So this is number 69 in your book. Right? So we can use, when we react to aqueous solutions, we can use molarity to show us how they react. So, first thing we always need to do in stoichiometric questions like this is to find the number of moles. If you're given moles, then they've already done the first step for you. So again, it's liters times molarity. So this is for KCl. So it's liters. So remember, you're going to divide by 1,000 times molarity. So this is for lead 2 nitrate. So what we're going to get is we're going to get the number of moles. So I'm not going to add the descriptors. I would recommend you adding them because it helps keep the math separated and keeps everybody honest. So now, what do we need to do if we're going to try to figure out which one is the limiting reagent? Because that's what we want. We want limiting reagent and we want theoretical yield. So let's use the lead 2 chloride as our product. And usually if you have a precipitation reaction, then use the solid as your product that you solve for. So we know for every 1 mole, or for every 2 moles of potassium chloride, you get 1 mole of lead 2 chloride. And here it's a 1-to-1 ratio. Okay? So, again, because we're looking for theoretical yield, I'm going to do it one more step further. So for every 1, oops, I switched these. So the lead chloride needs to be on top. Here it doesn't matter much. On the bottom it doesn't matter because it's a 1-to-1 ratio. This one will matter. So we need to switch those. So lead 2 chloride needs to be on top because we're going to then find the grams of lead 2 chloride. And to do that, we need to put the moles on the bottom. So, I'm going to erase this again, like we did before. So, once we get that done, we can do the calculation and we can find that potassium chloride gives us 4.172 grams of lead 2 chloride. And lead 2 nitrate gives us 3.75 grams. If you've noticed, I changed the answer here to match the significant figures that were given up here. So, 3.75 grams is the theoretical yield. It comes from lead 2 nitrate, which is the limiting reagent. Now, I want you guys to calculate on your own. I'm not going to put it in here. Let's say you did this in the lab and you got 2.45 grams of lead 2 chloride back. What would be your percent recovery? So, There's one more different type of calculation we can use with molarity. There's a couple. The first one I want to cover is number 63. So number 63 is known as a dilution. So in lab, what we normally do is make a really concentrated solution. And so what we have is 12 molar nitric acid. And so 12 molar nitric acid is very concentrated. And so we have 50 mils of that. We want to know how many mils we dilute that in to make a 0.100 molar nitric acid solution. So we're going to do a dilution. So we're going to take our concentrated acid and we're going to make it more dilute. So to do that, we need this equation. M1V1 equals M2V2. If you ever see the words dilute or concentrate or make a new solution, those should be red flags for us to use this equation. And so how do we use this equation? We take the molarity of our solutions, and it's arbitrary, it doesn't matter which one you pick. We take the volume of the other, it does not have to be in liters, it can be left in mils, times the molarity of what we're going to make, times the volume, usually what we're trying to find. When we solve this, so we just solve it, V2 is equal to 6,000 mils or 6 liters. Now, that is the answer. So to make this dilution, to make 0.1 molar nitric acid from 12 molar nitric acid using 50 mils, you would put 50 mils of the 12 molar into 5,950 mils of water. And so that's what it means to dilute something, is we're adding water to it to bring down the concentration. So, for Wednesday, the 19th, I want you guys to do number 64. I just want you to try it. We're almost done. I'm going to just show you the equation. H2SO4 aqueous plus sodium hydroxide goes to water, because it's a acid-base reaction, plus a salt. So we have 45.7 mils of 0.5 molar sulfuric acid. We use 20 mils sodium hydroxide to get what's called the equivalent point. So when we do acid-base titrations, which is what this is, and we'll go over this a little bit more in class, when we do titrations, we hit what's known as the equivalent point. And what that is how much base it takes to react with how many moles of the acid, to where you equal them out. And so we want to know, if we use 20 mils of base to react with this much acid, what is the concentration? So, the first thing we need to find out is how many moles of H2SO4. So we decided, if you're given a volume and you're given a molarity, you multiply them together and you will find the number of moles. Alright, so here's our molarity. We're going to go ahead and do the conversion in liters. And so we're left with 0.02285 moles of the acid. So when we reach the equivalent point, this is how many moles of the acid there are to react with, that the base will react fully with. So we have to use our molar ratio one more time. And what we do, so for every 1 mole of acid reacts with 2 moles of base. And so now the number of moles of base that have to react with that much acid is this, right here. But we're not done yet, because we want to know the concentration. So we know moles, we know the amount, we can just divide them. So let's go ahead and get us some space. So we have 0.0457 moles. We're going to divide that by 0.0200 mole, or mils, or liters, sorry, because we converted it. When we do that, we are going to get 2.28 molar sodium hydroxide. So all of the calculations, with maybe the exception of some of the molarity calculations, it's all the same theme. Turn it to moles, use the mole ratio, find the product. Or turn it to moles, see how much can react, go back to calculate how many grams are left over. So again, we'll practice this more in class. I understand these videos are a little bit long and I apologize, but with this introduction, we can now spend more class time doing problems. I hope you guys get some stuff out of the practice that we're doing, and I will see you guys later.